Hello everyone and welcome to this week's lightweight Java game library 3D game tutorial, and this week we're going to be adding specular lighting to our game engine so that we can make objects look shiny if we so please. So what is specular lighting and what does it look like? Well, last week we worked on diffuse lighting, which looks like this, where the brightness of the object's surface depends on how much it faces the light. Specular lighting on its own looks like this, but we'll be calculating it and then adding it to last week's diffuse lighting to give a final result like this. You can see that the addition of the specular lighting gives the objects a shiny look and feel. So specular lighting is not something we use instead of diffuse lighting, but we use it in addition to the diffuse lighting. But what is specular lighting? Specular lighting is reflected light on shiny objects, and in many ways it's basically just the reflection of the light source in the surface of the shiny object. So let's imagine that this here is the surface of a shiny object, and that there's a light source here. Let's now work out what the specular lighting would be like at this point here, which would have a surface normal like this. Light will come down in this direction from the light source and hit the vertex. Now, not only will the point be lit up with diffuse lighting that we calculated last week, but because this is a shiny surface, some of the light will be reflected off like this. Hopefully you can see how the reflected light corresponds to the incoming light ray and the surface normal here. If you imagine the light source being here instead, the light would be reflected like this, or if the light source was here, then obviously it would be reflected like this, and so on. The amount of light that's reflected depends on the reflectivity of the surface, so we're going to be representing this in our code by giving our entities a reflectivity attribute. If the object has a high reflectivity, then the reflected light will be stronger, and if it has a low reflectivity, then the reflected light will be much weaker. If the object has a reflectivity of 0, then no light would be reflected at all, and there would be no specular lighting. The brightness of this point also depends on one final factor, and that is the position of the camera. If the camera is positioned here, then the point would have a very high specular brightness, because the reflected light is going straight into the camera. If the camera is positioned somewhere like here, then pretty much none of the reflected light would go into the camera, and so the point wouldn't appear any brighter than a completely non-reflective surface. It wouldn't have any specular lighting at all. Finally, if the camera was here, it would probably get some of the light going into it, and so the point would have a bit of specular lighting, but it depends on the material. So we're going to have another attribute called shine dampening, which determines how close the camera needs to be to the reflected light to see any change in the brightness on the surface of the object. So let's now go into the code and create these two attributes that I was talking about. So in the model texture class, we're going to add the shine damper, which we're going to initially set to 1, and we're going to add the reflectivity attribute, and we'll set that to 0 to start with. We then need to create some getters and setters for these two attributes, so select both of them and click OK. Let's now go into the fragment shader and let's create two uniforms for these shine attributes. So one uniform float for the shine damper and one uniform float for the reflectivity of the material that's being rendered. Now in the static shader we have to do our usual thing, and we have to create two variables here to hold the location of those uniform variables that we just created in the fragment shader. So one will be location of the shine damper and one will be the location of the reflectivity uniform. Let's now get the location of these two uniforms like we always do using getUniformLocation. So we do that once for the shine damper and once for the reflectivity, and make sure you spell the uniform variable names properly there, because if you don't it won't work. Then we need to create a method to allow us to load up values to these uniform variables. So this is going to take in the damper value and the reflectivity value that we want to load up to the fragment shader. And then we can load these values by using loadFloat, putting in the location of the uniform, and then putting the value that we want to load to that uniform. So we do that once for shine and once for reflectivity. And I also need to spell float correctly. Then in the renderer class, before we render something, we need to load up those values every time we render an entity. We need to get the texture and get those two shine variables and load them up to the shader. So let's do that here. We're going to call shader.loadShine variables and put in the two shine variables from the texture. Let's now have a look to see how we can calculate the specular lighting from these variables in the shaders. So at any given point on the object we have the normal vector and the toLight vector, both of which we got in the previous episode. For the specular lighting calculation, however, we're going to need the direction of the incoming light, which is the vector from the light source to the point on the object. And obviously this is just the opposite of the vector pointing to the light source that we had last week. We will then reflect this light ray to get the reflected light direction, and we also need one more vector, which is a vector from the point on the object to the camera. So as I explained earlier, the point will have the brightest possible specular lighting when the reflected light ray goes directly into the camera. When that happens, these two vectors will be pointing in the exact same direction. If these vectors are far apart, it means that the light isn't going into the camera at all, and so the specular lighting of that point on the surface will be very low. Basically, the closer these two vectors are together, the more the reflected light is going into the camera, and therefore the brighter the specular light at that point. So, we need to find out how close these two vectors are to pointing in the same direction, and hopefully you'll remember from last week that this can be done using the dot product. So, by taking the dot product of these two vectors, we'll have an indication of how bright the specular light at that point on the surface should be. We can then use the shine dampener attribute of the material to dampen this value, and then multiply it by the reflectivity of the surface, before finally adding it to last week's diffuse lighting to get the final result. So let's start off in the vertex shader, and the first thing we need to do is to create the out vector, which is the vector from the vertex to the camera, which we'll call toCamera vector. Now you might think that we would calculate this in the same way that we calculated the toLight vector, by subtracting the vertex's position from the camera position, but we don't have the camera position anywhere in the shader code. What we do have, however, is the view matrix, which, if you remember from a few tutorials ago, contains the negative version of the camera's position. So we need to take the inverse of this matrix and apply this transformation to a 0, 0, 0 vector to convert it to a 4D vector, and this is now the camera's position. Now we can get the vector from the vertex to the camera by subtracting the vertice's position from the camera's position. Let's now move into the fragment shader, and the first thing we need to do here is to take in the toCamera vector, that's the vector pointing to the camera. Then, like we did with all the other vectors, we need to normalize this vector to make sure that the size of the vector is just 1. Once we've done this, we also need to create the vector that points in the direction that the light is coming from. So that's the light direction, and this, as I said earlier, is just the opposite of the vector pointing towards the light that we had last time, so let's just make that negative. So we now have the light direction vector and the vector pointing to the camera, and of course the surface normal. So all we need now is the reflected light vector. Thankfully, GLSL has a reflect function to do this for us. This function takes in the incoming light vector and the normal of the surface that you want to reflect the light with, and it returns the reflected light direction. So let's now do this in the code. We're going to create a reflected light direction, and we're going to do that by using the GLSL reflect function, and that takes in the light direction and the normal of the surface that we want to reflect the light in. So now we have these two vectors, and we can do the dot product calculation to see how much the reflected light is going into the camera. So let's dot the reflected light direction and the vector to the camera to see how similar they are, and that returns the float, which I'll call specular factor. And this indicates how bright the specular light, without any dampening, should be. And we also have to do that thing we did last week to make sure that the specular factor is greater than 0, because obviously we can't have a negative brightness. Let's now apply the damping of the material, and we do this by raising specular factor to the power of the damping value, which makes low specular factors even lower, but doesn't affect the higher values as much. All we need to do now to get the final specular light value is to multiply it by the light color, so that the specular light is the color of the light source. And we do that just by doing damped vector multiplied by light color, and that will return the 3D vector called final specular. We then simply have to add this to the diffuse lighting, and of course we first have to make it into a 4D vector, because out color is a 4D vector, not 3D, because it's an RGBA color, not just RGB. So let's go into the main game loop to finish this all off. So we need to get the texture so that we can set the shine variables to it. So we can get it by doing static model.getTexture. Now let's set the shine and the reflectivity. So first we'll set the shine damper, and I'm going to set that to 10. You can play around with these values to see what looks best. And I'm going to set the reflectivity to 1. So let's go ahead and run that, and there you go, the dragon is looking very shiny and pretty nice. So as I was editing this video, I realised that I never used the reflectivity value in the fragment shader, so you need to add that in to the final specular calculation, and all you have to do is multiply it in here, and that should now work perfectly. So that is it for this week. If you haven't seen yesterday's devlog video, then a link for that is on the screen now, and this week I was just demonstrating the finished entity editor. Don't forget to follow me on Facebook and Twitter, links are in the description for all my social media sites. But yeah, thank you guys very much for watching this video. Do subscribe if you haven't already. Have an awesome week, and I will see you all next time.